All right, I think that's the high sign. Thank you all for coming. 2 years ago, as you all know, there was a horrific earthquake. 2 weeks ago. Yes. 2 weeks ago, what did I say? 2 years ago? Yeah, time flies when you're having fun. 2 weeks ago, there was a horrific earthquake off the east coast of Honshu, which launched a tsunami and the ongoing crisis of recovery from that, including the nuclear power center. It has launched a whole lot of misinformation, I would say, on the internet and in the press, and it seems that occasions like this, it's important for us to take the opportunity to try to get across at least the parts of the physics and the geophysics that we understand. The crisis is ongoing in the reactor, and I don't have a direct line to Tokyo Electric Power, so I will try to describe in general what we understand after Greg first talks about the geophysics of it. But I want to make an announcement. At the end of the presentation and discussion, there's a group at the 5 colleges raising money for victims of these events, and they will be stationed in the foyer afterwards if you are interested. So I'm going to, the chronological order of things is earthquake, then tsunami, then nuclear catastrophe. So I'm turning it over to the geophysicist Greg Lyzenga.
Okay. Thank you, Peter. As Peter suggested, I think the right order to talk about these things is the chronological order. And so I understand that many of you are probably most interested in sort of hearing about and discussing the ramifications of the nuclear accident. But so I'll try not to overstay my welcome here, but I think that there's a lot of curiosity and a lot of interest in becoming educated about the facts of earthquakes in Japan and what relationship those might bear to earthquakes that we can expect in this part of the world. So, so that's my intention here, is to try and give you a quick overview of what we know. Thinking now about 2 weeks ago tonight, our son, who is a jet teacher living just west of Tokyo near Mount Fuji, called us up on his cell phone and asked us, "Are you watching the news?" And we weren't, but we quickly flipped on CNN and were pretty shocked by what we saw. And it was clear after a short period of time that there was a very, very significant event unfolding. And so what was happening is what we now know as the Great Tohoku Oki earthquake, a magnitude 9 event. And I hope to tell you in a little bit just what that means, what that magnitude 9 means. We did record it, obviously, here in the seismology lab at Harvey Mudd. This is the record from our broadband seismometer, and I don't expect it to mean a whole lot to you. It's a lot of wiggly lines. But it's interesting, the scale here shows that the ground here in Claremont moved about 1 centimeter as a result of the earthquake waves passing by. But the peak velocity was only about 1 millimeter per second, so that was not an acceleration that was appreciable to human beings. But it's a very large amplitude of motion for an earthquake, particularly so far away. So as many of you are probably aware, this event was a manifestation of global plate tectonics, and so we'll begin with Plate Tectonics 101. And illustrate for you the fact that we live on the edge of the Pacific Plate, this so-called rim of fire around the Pacific Plate. And as the Pacific Plate moves, it gives rise to coupling and then earthquakes and other kinds of events like volcanic eruptions where these boundaries occur. Here in California, we have a strike-slip boundary, which means that the plates are moving laterally past one another. But along much of the Pacific Rim, along the Aleutian Islands, along the Kuriil Islands and the Kamchatka Peninsula, the Japan Trench, and so on all the way around, there are subduction zones. So what is a subduction zone? It's a zone where one plate is basically colliding with and diving underneath the other. So in this diagram, it's kind of turned around backwards. This would be the Pacific side, and this would be the Japan side. And the Pacific plate is diving underneath Japan. And the frictional rubbing or coupling between the two plates that occurs at this slanted interface here gives rise to earthquakes, as well as the volcanoes that we see manifested in the majestic peaks like Mount Fuji. So it's this sort of stick-slip boundary right here that is what's responsible for the very large earthquakes that are characterizing Japan, as well as other subduction zones around the Pacific Rim. Here's a little bit of a close-up of the geometry of the plates in the vicinity of Japan. Here's a 3D perspective view that shows it's actually kind of complicated. It's not just two plates. There's the Eurasian plate. There's actually a little finger of the North American plate that kind of makes its way across the Bering Sea and comes down here. The Philippine Sea plate, and then here's the Pacific plate, which is pushing underneath the landmass of Japan. And on the right here is a little cartoon diagram that shows the mechanics of what's happening in that process. As the plate pushes under, it's locked right here on this interface until the frictional strength is exceeded, and then a sudden jerk occurs. I've got actually here a little animation that I can show you that will sort of give you a view of that process. Let's see, bring this up. So what I'm going to point out to you is that there's a time scale down here on the bottom that initially is graduated in years, which is the period between earthquakes, and then it switches to minutes when the earthquake actually occurs. But here you can kind of see visually the process by which the oceanic plate is trying to push back the continental plate here, but it's locked by friction. And as it pushes, it deforms the margin of the overlying plate, compressing it. Then the earthquake occurs, releases the stress, and moves the ocean floor, displacing water and causing the accompanying tsunami. So that's just a little sort of cartoon view, a cartoon illustration of what is happening. Oh, sure. It's not a long movie. You can play that again. So here we go. We're right now in the accumulation phase. You see 100 years, 150 years. The stress is building up, and then the rupture occurs, pushing the island back up and displacing water and causing the wave in the ocean above. And if you're not aware of the fact, the waves that travel in this ocean here are basically very long in wavelength in comparison with the depth of the water, which basically means that they travel at hundreds of miles per hour. So there's very little delay in minutes between the formation of this tsunami and the time before it hits the nearby coast. So that's one of the reasons why such tsunamis are so deadly, is because if you live very close to the hypocenter of the earthquake, there's not a whole lot of warning time to get to higher ground. Okay, was that enough of a replay? Whoever that again. Well, there's more stuff to show you. So if you want me to play it again at the end after Peter gets a chance to talk to you, I'll be happy to play it again and give you links to these things as well. So I wanted to, even though it's a little out of sequence here, I wanted to insert a little comparison with things we might be familiar with, because this is a very large earthquake. And one of the first things people often ask is, how likely are we to have a comparable event in Southern California? So to talk about Southern California, I'll just remind you of what our history is here. People often talk about the big one. There have been a couple of big ones in California history. The 1906 San Francisco earthquake ruptured a segment of the San Andreas Fault that was about from here to here. There's a section here that doesn't have earthquakes because it's creeping without friction. But then there's this southern segment which last ruptured in a great earthquake in 1857. And that's the one that's got most of us in this area nervous, since the repeat time for earthquakes on this segment is something on the order of 150 years. So it's probably due. So I wanted to kind of put some numbers to things. Being at Harvey Mudd here, I can get away with actually using quantitative measures of things, and the audience probably won't throw rotten fruit at me. So here is kind of an estimate of the biggest credible earthquake that we could have in Southern California. So this is that fault laid out sideways. You can see its depth is about 15 kilometers. That's how far down you can go before the material is no longer brittle. The length of that big 1857 earthquake was about 400 kilometers, give or take, and the slip amplitude was about 6 meters. So that's sort of the epitome of a large Southern California earthquake, the so-called big one. In seismology, we would quantify the size of an earthquake by multiplying three quantities together. The first is the stiffness of the rocks, which for typical rocks in the crust is about 30 gigapascals. Multiply that by the surface area of the fault, which for this case is 6,000 square kilometers, and then multiply that by the slip amplitude, which is 6 meters. So if I reconcile all those units to SI and multiply it out, I get about 10 to the 21 Newton meters for this quantity, which is called the moment of the earthquake. And since that's such a large and unwieldy number, seismologists have traditionally dealt with a logarithmic measure of the size of the earthquake. So the rule is you take the moment, you take its logarithm to the base 10, multiply it by 2/3 and subtract 6. So this is a magnitude 8 earthquake. So keep that in mind, keep that rectangle in mind, and see that that is a magnitude 8 earthquake, and that's the biggest thing that's probably ever happened in Southern California. Now, compare that with the Tohoku earthquake. On the same scale, here's the fault plane. All right? So it is about 10 times the area. Principally, it's about the same length. It's about the same 400 kilometers in length. But because it's on this slanting plane going diagonally through the crust, it's got a width of 150 kilometers. So this is 10 times the area, 60,000 square kilometers, and it moved by 3 times as much, by 20 meters on average. So this is a truly huge event, and so you go ahead and multiply the stiffness by the area, by the displacement. You get 3.6 times 10 to the 22 Newton meters, which is a 9.0. It's not the biggest earthquake that's ever happened. The biggest earthquake on record was a 9.5 in Chile in 1960, but this is definitely on the upper end of the largest earthquakes that can or have occurred. So, what does this imply? What does this mean? Well, obviously, a lot of shaking. But it also causes, in addition to those oscillatory shaking motions, it causes permanent deformation of the Earth's crust and of the Earth's overall figure. The moment of inertia of the Earth changed so that the rotation speed of the Earth has changed a measurable amount. Here's one of the observations that was collected shortly after the earthquake by my colleagues at the Jet Propulsion Laboratory. Japan is one of the most heavily instrumented places in the world. There are over 2,000 continuously operating GPS stations all over the nation of Japan. And these arrows show how much permanent deformation occurred as a result of the earthquake. The scale right here, that red arrow is 1 meter of displacement. So you can see a substantial part of Honshu moved by several meters to the east. And this is due to that sudden, abrupt slippage on the subduction zone. The blue arrows are actually due to an aftershock, or at least a motion after the main earthquake that occurred a few hours afterwards. These blue displacements are the equivalent of about a mere 7.9 earthquake. Would have been very significant if it hadn't occurred a half an hour after this. So I've actually got an interesting animated figure here that shows those GPS results as a function of time. There's a similar one to this that you can find on YouTube if you look for it. It's kind of entertaining to watch. But the time is going to be displayed down here in minutes. And what you're going to see is the arrows pop up and spread across the landscape as at the speed of sound, basically, as the displacements occur on the GPS stations, on the GPS network. So let me go ahead and start that animation. You can watch the time down here. The colors are coded to displacement amounts. So that's 1 meter, 2 meters, 3 meters, 4 meters, and so on. So you can see this develop. So let me find my cursor here. Here we go. Okay, so there's the rupture occurring, spreading across, and the arrows are showing the permanent deformation. So this is the hypocenter of the earthquake. Now watch right here, because a half an hour after the earthquake, that magnitude 7.9 aftershock is going to come and push Tokyo a little bit more. Coming up here in just a minute. There it goes, and now more. So more displacement. So this is basically the first time that I'm aware of in history that we've had this kind of an actual movie of the displacements accompanying a big earthquake like this. I'm going to move it along here so that Peter gets a chance to say a few words. But last week during spring break here at Harvey Mudd, I spent a good deal of my time actually performing numerical inversions on this data to try and figure out what the actual dimensions of the fault plane were. So I was working with my colleagues on that, coming up with preliminary models. There have been other people sort of throughout the geophysical community that have been doing similar things. Here's another result. This is a 3D perspective view that shows that the displacement on the fault surface is actually not uniform, but it's actually kind of rough. There are peaks and minima in the amount of slip, but you can see the highest amount of slip, this red, is over 25 meters. So that 20 meters that I quoted is kind of an average value, but it's actually even larger than that in places. And no doubt there will be people working for many months to come and refining these models and trying to figure out exactly what really happened. But we do have emerging at this point a pretty clear picture of the facts as far as the movement is concerned. Now, I should probably say a few things about the tsunami as well, so I'll do that very briefly. I have not got active research going on in Tsunami Genesis, but some of my colleagues do. And I've borrowed this animated graphic from one of my colleagues who did models of the tsunami generation from this event. So the event, again, is a rupture in this area right here. And when I start it up, you'll see the time going by up here in minutes. This would be, I think, seconds, minutes, hours. And you'll see the tsunami basically radiating outward. Not very many minutes are going to elapse before the earthquake occurs and the first waves hit the coast here near Sendai. So we'll go ahead and start that one up here. Here we go. So you can see the waves eventually making their way back into the Sea of Japan. It's now 20, 30 minutes after the earthquake. And they've got a version of that that's on a little bit larger scale here, so you can see the waves actually running across the entire Pacific. So there it is. It's now 4 hours, 5 hours, 6 hours, 8 hours. It hits Hawaii. Now it's on California coast. So that's the kind of calculation that's needed to be done in real time in order to do tsunami warning to people around the Pacific Rim. I guess I can point it out here. I'll run it one more time, that those numbers that appear, let's see, I have to go back again. Those numbers that appear are the run-up of the tsunami in centimeters. So you can see that we've got almost a 3-meter rise in Hawaii and 1.5 on the California coast there. So I'm almost to the end of my comments right here, and then we can decide if we want to have questions. But I thought I would put a little bit of this in a little bit bigger context first. One of the questions that often comes up is, was this anticipated? Well, clearly at some level it wasn't anticipated. I think that it was assumed by many people that since no great earthquake of magnitude 9 had occurred in this area in recent historic times, and by that I mean probably for at least 1,000 years or more, there was perhaps a false feeling of security. But it's not entirely the case that it was unanticipated. One of my colleagues pointed out to me this paper that was published in 1979, which anticipated the possibility of a large interplate earthquake in this spot right here. So, so there are certainly reasons to think that we could have anticipated this event, but there was by no means any scientific consensus on that possibility. I guess I'm going to discuss one more little thing that may be of interest to some of you. Go back to my Plate Tectonics 101 picture here and point out that, you know, in addition to all these subduction zones around the Pacific Rim, we have a little bit of a subduction zone in the United States. While we do have those skinny little faults that don't have much area in California, the Pacific Northwest has a great subduction zone right here, extending basically from the Oregon coast on up into the Puget Sound area. And so this is known as the Cascadia subduction zone. It has the volcanoes associated with it that we know and love, Mount Shasta and Mount Hood and Mount Rainier and all the great volcanoes of the Pacific Northwest. And it does have great earthquakes. There was a magnitude 9.0 earthquake in the evening of January 26, 1700. You may be wondering how I know that. I know that because the Japanese recorded the tsunami and wrote it down. So we know exactly when it happened, even though there was no one writing down history here in the Pacific Northwest at the time. There was a great event there, and we also understand that such great events do recur on time scales as short as 200 years and as long as 900 years. So it's now been 300 years since the last great subduction event here, and I think that it would, you know, be a good thing to think about if you live in the Pacific Northwest, to understand the potential for events basically exactly like the Tohoku earthquake on the west coast of the United States. So I think that's probably a good place for me to stop. And are there any, before we sort of switch over to talking about the nuclear disaster, are there any questions you want to ask? Yeah?
There was an earthquake in Alaska.
Mm-hmm.
It was about 1964, 65.
That's right.
That doesn't fall into this category?
It does, actually. I'll go back here and show you where that was. That was here in the Aleutian Islands Trench, actually kind of right in this corner here in Prince William Sound. That was, I think, a 9.2, so that was very definitely in this class of earthquake, a great subduction earthquake. I don't know if you remember, but it caused a destructive tsunami that caused a lot of problems in Crescent City, California, and I think also in Hawaii as well. So,
odd story, if I may tell it just a moment. I was driving from Baton Rouge, Louisiana, back to Dallas, Texas, and any of you who have been in the South Louisiana area know that the road runs right along the bayou, and the bayou is green with algae, never moves.
mm-hmm.
As I was driving around by there, the bayou sloshed from the aftershock.
That's pretty neat.
Kind of stopped and was wondering what was going on.
That's quite a story. Yes?
I'm just wondering, for the equation, calculating the magnitude of an earthquake, you're like incorporating the stiffness of a rock.
Yes.
I'm just wondering why it wasn't the same for California versus Japan.
Well, that's right. I think you should probably realize that all these magnitude determinations are actually kind of order of magnitude. You could change the value assumed for the stiffness of the rocks by 10 or 20%, and it would hardly change the magnitude at all after you take the log. So you should take those numbers with a grain of salt. There's a reason why when the earthquake is first reported that a week later it changes. It's because these numbers are not extremely well determined. And so, you know, those numbers that I put up there were kind of off the top of my head, but they aren't going to change the final magnitude very much. Good question. Yes?
Is there any kind of relationship between the Christchurch New Zealand quake and those events happened pretty close to each other at the time?
Right. One of the things I'd meant to say was that, you know, when I was comparing magnitudes, was I was going to point out that a 7.0 like the one that happened in Haiti is, in terms of moment, 1,000 times smaller than the Sendai earthquake. Okay, so they take 1,000 Haitis to make one of these Japanese earthquakes, and the one that was so damaging in Christchurch was only about a 6, and so now divide that by another factor of 30, and you get an understanding that what makes for a disaster isn't always a huge earthquake; it's location, location, location. And so in the case of the Christchurch earthquake, it was sort of in the landmass of New Zealand. You can see that New Zealand is not far from subduction zones here. The Tonga Trench is nearby. But this map isn't quite detailed enough to show it. New Zealand is kind of in a zone of tectonics very much like California, where there's side-to-side motion connecting these two areas to the north and to the south. And so what happened in Christchurch was probably most analogous to the kind of things that we could expect here in Southern California. Mm-hmm.
Should there be any credence given to people saying, like, talking about earthquake predictions? Because some of the news stories that came out after the earthquake was people saying, like, oh, there's going to be an earthquake in California soon, or oh, there's going to be big earthquakes in, you know, the United States. Because you look at Christchurch and you look at Japan, you're like, oh, it's moving around the Pacific Rim, so it's going to come down to us. So I just want to know, like, what on the scale from complete quack to like legitimate concern do we put those type of predictions?
Yeah, you have to parse such claims very carefully, because there are certain kinds of statements you can make that are valid. Like you can say, well, yes, there's going to be an earthquake someday in California or in the Pacific Northwest. And you can even begin to forecast those in the sense that you can apply probabilities. And you can say, okay, based on our knowledge of the rate at which stress is accumulating, we can assign a probability that it's going to occur in the next 300 years or in the next 100 years, something like that. So those kinds of statements are based in good technical, good scientific reasoning. But the kinds of claims that you're referring to, which really sound more like astrology than anything else, those are not reasonable. There's no credible scientific reason to believe that, you know, there's some kind of a, you know, beast that's walking around under the earth that's walking from spot to spot and popping things off. It's just not, that's not credible. So, yeah, I don't know. Did I kind of address your question?
Yeah, I think so. I guess they often, like, at least in the articles I read, they talked a lot about like tidal forces and like the moon and
right.
Talking about gravity issues.
Yeah, I mean, typically those sorts of arguments use very scientific sounding words. But when you actually look at the magnitudes of the things that they're talking about, you look at the tidal stresses associated with, you know, we had the supermoon, I guess, last month, right? The really close near full moon. You look at the actual size of those and you realize it's just in the noise compared with the actual magnitudes of the stresses involved. So there's no reason to believe that any of that is actually credible. Mm-hmm. I was ready for that question. Here on March 9th, there was a 7.2 that occurred in the zone of the earthquake that would happen 2 days later. At the time that it happened, I don't really actually remember if I took great notice of it. Usually when a 7.2 happens someplace in the Pacific Rim, I do notice it because it makes a pretty good record in our seismology lab. But I don't know that anyone thought that it was particularly ominous. Sevens have been occurring over the last several years in the general region of Japan for quite a while, for decades, and so it's not, I don't think, something that set off anybody's alarm bells at the time. In retrospect, it's obvious that this was causally related to the 9 that happened right after, 2 days later. But it's very difficult to be able to look at an earthquake. I'd say it's impossible to look at any given earthquake and say, oh, that's a foreshock, get ready. So, it's interesting, but I'm not sure that we could have done anything that would have predicted what would follow. Mm-hmm. Mm-hmm.
I'm curious, I can see up here that this particular foreshock was 32 kilometers in depth, and I'm not sure how far off it goes. But if a magnitude 9 had actually occurred on the land mass, as relatively happened from the ceiling, that would have presumably led to a lot less damage.
Well, a lot less tsunami damage. By the nature of subduction zones, they almost always occur underwater, which I guess you could say is a good thing and a bad thing. It's a good thing in the sense that, well, you know what? I'm going to actually retract a little bit of what I just said. There's a certain level at which it doesn't matter how big an earthquake is if you're right on top of it, because getting bigger for an earthquake just means getting larger geographically, and so it gets farther and farther away from you. So I'd be just as concerned about being on top of a magnitude 6 or 7 as I would be on top of a 9, because the 9 would still have substantial parts of the energy release that were hundreds of kilometers away from me. So from a standpoint of shaking, I don't think it makes a whole lot of difference. But of course, from a standpoint of tsunami generation, it's all about displacing water. And so the fact that these big subduction earthquakes move the ocean floor and displace water is what makes them so destructive as far as the tsunami is concerned. Did I kind of address the question? Okay. Mm-hmm. Oh. I don't know the answer to that question. I was sort of assuming that there were tide gauges that were reliable, that were able to actually provide that data. But I'm not familiar with the agencies that are kind of in charge of that information. So I don't have the answer right at the tip of my tongue to your question. Mm-hmm.
Sorry, one last question. I've heard about something called the elastic rebound theory, where you have slow growth of earthquakes over time, and then you have big ones, sort of like what happened in the San Francisco earthquake.
Mm-hmm.
Can you see that in this scenario, where you have like a buildup? You said you were seeing a couple, like a growth of 7 earthquakes, and then you see the big one. Or is that not reported?
Well, that's a very complicated question to answer, because there's really no two regions in the earth that behave exactly the same. Sometimes you'll have regions that do sort of presage their failure with lots of creaking and popping and preliminary events before the main shock occurs. But you can also, as you pointed out, the geology is different, the rocks are different from place to place. You can have places not very far away which rupture basically without warning. And so the Earth is a heterogeneous place. There's a lot of variability in the way it behaves. And so that's really what makes earthquake prediction such a difficult thing to pursue, is something that works in one area might not work well at all in another. Shall I turn the floor over to Peter? We can entertain more questions about this later, but give Peter a chance to. disconnect here. You want to use that?
Yeah, I might as well.
Okay.
Sorry. Right there. You were just testing me. And did you bother plugging in power? Well, I should be okay power-wise. Thanks. Okay, so whereas Greg is a bona fide geophysicist, I'm just a schlub, but I've been trying to bone up a little bit, and I've been teaching a course on energy and the environment, which has brought me into worrying about nuclear power and storage issues for the waste from nuclear power. And it just seemed to me that it's really important to try to make sure that we don't argue either for or against nuclear power for the wrong reasons. Let's not huddle inside the cathedral to avoid the bubonic plague. So this is a picture of the plant in Fukushima Daiichi. There are 1, 2, 3, 4 of the older reactors and 5, 6 over here. It was designed for I believe the claim was a 7-meter swell of a tsunami, and as the gentleman pointed out, the recent data suggests that it was a 14-meter swell. So it clearly overwhelmed the seawall and flooded in, which disrupted all sorts of safety and backup equipment. This is what I wanted to try to talk about, and then I can do my best to field questions that you may have. So I just want to introduce what is the basics of radioactivity, why is it damaging, how does it influence, or how does it interact with biological tissue, how do the reactors there work, and what are typical levels of radioactivity at reactors or around here. Now, the previous accidents of consequence are 3 Mile Island, which happened in 1979 in Pennsylvania, and the Chernobyl in Ukraine. And so I'd like to talk just a little bit about the consequences of those. And finally, let's worry about the relative magnitude of damage. So first step is, what is radioactivity? And it's just the emission of one or more energetic particles from a nucleus that looks around and decides, if it's a spontaneous radioactive event, that it could lower its energy by falling apart, typically. And the extra energy in falling apart and going to a more stable configuration is released either as an alpha particle, which is just the nucleus of helium, beta decay, either an electron or a positron, gamma radiation, which is just light but very energetic, could be neutrons, and then in the case of fission reaction, where you start with a very large nucleus, you come up with various fragments, which are other nuclei, many of which are radioactive themselves. And what we're focusing on is that the particles coming out, alpha, beta, gamma, neutrons, are energetic enough to break molecular bonds. So they are able to produce ions that then can go and attack things like your DNA. And it's that which causes the damage. Oh, I should have said, pardon. In the air, a piece of paper is quite sufficient to block alpha particles. They do not penetrate very well. And if I had an alpha emitter sitting here on my hand, it would be no problem, because the skin at the outer surface is dead. The living skin is underneath, and the dead layer of skins is enough to block the alpha particles, the fictitious ones that I've got right there. Beta particles are typically a little bit more penetrating, and you can block them with some aluminum. And gamma rays, depending on their energy, can go through several centimeters of lead and require the greatest shielding. So what is it, what causes it? Well, some people have argued that when the Earth was formed from the debris from a previous star, that most of the nuclei, most of the atoms were radioactive, and the only ones that are still radioactive are the ones that decay very, very slowly, the other ones having already decayed into things that ultimately produce stable nuclei. So the uranium that's left over is still around because it falls apart so very, very slowly. That's for spontaneous radioactivity. Another approach for producing radioactivity would be that it's regenerated by cosmic rays at the top of the atmosphere. So our atmosphere has mostly nitrogen. Nitrogen, when it's bombarded by energetic particles in the upper atmosphere, can become nitrogen, which is normally atomic mass 14, becomes carbon-14. And carbon-14 decays with a half-life of about 5,700 years. And, of course, it's produced up in the upper atmosphere at approximately a steady rate, and therefore the fraction of the carbon in the biosphere is constantly being replenished by that production mechanism. And since you are a carbon-based life form, in a typical human, you have about 3,000 radioactive carbon atoms disintegrating per second. So you are radioactive. And you also have radioactive potassium, and stoking up on a banana, which I am told is a very good thing to do, also ups your radioactive potassium. But you are designed to handle that. So let me just make sure that we're clear on what a half-life is. So iodine, one of the worrisome species coming out of the nuclear reactor is iodine-131. It has a half-life of a little bit more than 8 days. And so if I imagine having almost 1,000 radioactive iodine-131 nuclei on the first day, after 8 days, half of them will have decayed. And after 16 days, another period of 8 days, they will be down to about 256. And after 80 days, or 10 half-lives, on average, only one of these radioactive iodine atoms is still around. Now, that radioactive iodine, because of the way the body functions, or iodine in general will concentrate in thyroid. And so a precaution that is advised for the Japanese living near the reactor is to take a salt of not radioactive iodine, so tablets of potassium iodide, to saturate their thyroids so that they will not be in any mood to take up more iodine, none of the radioactive iodine, and therefore avoid having a concentration of radioactivity in their thyroids. Now, I am told that these salt tablets have sold out in California. I guess you never can be too prepared. I have heard, however, that you run more risk of causing problems to your thyroid by ingesting too much iodine than you certainly do with the radioactivity. I'll discuss later the levels of radioactivity that we've been seeing from Japan, and it is definitely not yet time to panic. But I need to introduce first some of the units that we use to describe the level of radioactivity. And these have been changing in the same, well, almost the same way that pounds yield to newtons or kilograms, depending on what you're talking about. I'm going to emphasize the SI units for radioactivity and try to remember to mention what the older ones are, which are still often used. So the SI unit of radioactivity in a human tissue would be a gray. So a gray is when 1 joule of things like X-rays or gamma rays, so energetic light particles, is absorbed in 1 kilogram of tissue. So is that a lot of energy? Well, not really. I mean, if you just put in the heat capacity of water and figure that you are basically water, I did talk about the carbon, but primarily you're water, then that's the amount by which that radiation is raising your temperature. You will raise your temperature way more by sitting out in the sun. So that's not what's causing the damage. If, on the other hand, it is not light that is being used, but it's electrons that are being, whose energy is deposited in your body, that's 10 times more effective at causing damage. And so we scale up to, it only takes 1/10 of a joule of energy deposited by electrons to cause the same damage as 1 gray of light particles. And alpha particles, those helium nuclei, are even more damaging. And there's a little bit of dependence on the actual energy of the particle, but these are reasonably good rough numbers. Since we're mostly worried about the consequences for people, the sievert is the SI unit that describes the dose equivalent of 1 gray of X-ray. So it tries to take into account the relative efficiency of causing damage by the different particles. And 1 sievert, you may have heard of the word rem or millirems, which stood for or stands for Röntgen equivalent in man, and the sievert is just 100 of those. And so that's why I guess why it gets a capital S. It's bigger. So what happens when this ionizing radiation is absorbed in the body? So it's strong enough to break the bonds, which tends to form things like oxygen ions, which are very chemically active and can go and attack DNA. The damage of a charged particle plowing through a strand of DNA can knock out nucleotides. And in low dosages, what typically happens is that there are repair mechanisms. The double-stranded DNA has a template for using to perform the repair. As long as you haven't blasted too big a hole, the enzymes can come along and put back together the DNA strand. Sometimes they make mistakes. And typically what happens when they make mistakes is that the cell will end up committing suicide. In rare occasions, the restitching causes a change in the order of the DNA, which leads to cancer. At very high dosage, and that can happen in any kinds of tissue, at very high dosage, it affects the bone marrow and your ability of your blood to replenish itself in extremely high doses. And so this is where we're going to get to the number I want you to hold in your head. At extremely high dosages, over 8 sieverts, full body dose in a short time will lead to death within a matter of hours. At half of that, at about 4 sieverts, if you get prompt radiation treatment, the recovery rate goes up a lot. So the one number I want you to carry around, 3 sieverts is lethal dose 50%. That is to say, if 100 people receive 3 sieverts full body each in 30 to 60 days, 50 of them will have died. So 3 sieverts is the lethal dose, 50. Remember that number. These will help. You want to look, I guess, more like that than like that. At least that's my view. Okay, so recently, but some of you may be Picasso fans. Recently, there was a very nice chart put together. This is the URL, and I'll tell you where all these things are posted, should you wish to look. This was actually done on XKCD and is making the rounds, and it's trying to show what different levels of radioactivity we experience in daily life are, starting from the fact that I happen to be married. I sleep in the bed next to my wife. She, as I've told you before, is radioactive. I told you you were radioactive, and so I get a dose of extra radioactivity because I'm married. A banana has 0.1 microsieverts from mostly the radioactive potassium. If you get a dental X-ray, that's about 5 microsieverts. Now, Colorado, anybody from Colorado? Yeah. The rugged and tough people from Colorado, because the soils in Colorado are richer in uranium than typical in the United States. The background level of radioactivity is higher in Colorado. As the uranium decays, it eventually produces radon. And radon is a noble gas that is quite heavy. And in basements in Colorado, the radon gas will collect, and it's an alpha emitter. Now, I told you before that if you have an alpha emitter sitting here on your hand, it's not a problem because your skin will block the alphas. But when you breathe it in and it's in your lungs have to have very little barrier in order to have the oxygen and the carbon dioxide diffusing across that. And that's where the damage comes. So houses, when we built a house in Colorado, we had to make sure that there was enough circulation of air through the basement to keep the background level of radon at an acceptable level. So a normal day exposure, 10 microsieverts, you would have an exposure of not 10 but 11.2 if you're a hardy soul from Colorado. If you hop on a plane and you take a flight from LA to New York, or I think it stands to reason the other way around as well, you get an extra special dose of 40 microsieverts because you have less atmosphere protecting you from cosmic rays. So that's like 4 times your daily dose. The extra dose per day so far, this was made a couple of days ago, in a town near Fukushima was about 4 microsieverts. So 1/10 of a flight. Which brings up, so my son is currently in Beijing. He flew over earlier this week, and he squeezed a dental appointment in before he left. And when the hygienist found out that he was going over to China, she wanted to know if he was very worried about the levels of radioactivity. I mean, aren't they very close? Like, how long would it take to drive from Beijing to Japan? He just thought that was sad, that her geography was that good. So let's now talk about your annual dosage. And potassium in the body, so potassium 40 is a radioactive isotope. It's not very common, but it occurs at some small fraction in potassium. And that contributes 390 microsieverts. The EPA limit for exposure to the public from man-made events is 1 millisievert per year. If you take, however, a mammogram, you get 3 millisieverts. A chest CT scan is almost up at 6 millisieverts. Now, the maximum external dose from the 3 Mile Island incident was 1 millisievert. How many of you knew that? Okay, now we have to worry about what kind of damage if you have more radioactivity. Clearly, if you get 8 sieverts, you're a goner. So, and if you had 3 sieverts, you were 50% goner. And these are the data, the most intensively studied population are the survivors of the Hiroshima and Nagasaki atomic blasts. And the study continues to this day. This is the 7th report of the biological effects of ionizing radiation group. And this is the excess risk of a solid cancer, and this is the radiation dose in sieverts. So a lot of people died in those blasts immediately from the concussion, from just the mechanical effects. Another bunch died from that radiation overdose and getting radiation sickness and their blood systems shut down. But only on the order of 4% of the people around have died of cancer. And that group is studied in order to understand the effects of radiation. So if I look at a dose of 1 sievert here, I see that that provides an excess risk of about 4.5% over a lifetime. So what would I need to get up to 100%? So that's about 22 sieverts to cause 1 cancer on average, if this linear model is correct. Now, there's a lot of argument about exactly what's happening down here in the low dose range. Some people argue that your body is designed to repair the damage from an occasional radioactive event. After all, as I mentioned, you have about 4,000 of them by the time you consider the radioactive carbon and potassium going off in your body all the time. And if we hadn't evolved a way to deal with that, we wouldn't be here. So some will argue that below a certain threshold, there is no risk. There is no damage caused that. And it's only above that threshold, although this group still argues that there's no convincing evidence to say that, to persuade them to use anything but a linear model. So I now want to turn quickly to what happened in those previous incidents. So in 3 Mile Island in 1979, the pump supplying the cooling water failed. A valve to the backup pump was accidentally left closed. I mean, it was just a cascade of mistakes. Control rods were inserted, but as I will describe, as the reactor operates and the uranium decays, it produces all sorts of fission fragments because a big nucleus can fall apart in a lot of different ways. And a lot of those fragments are themselves radioactive. They have their own half-lives, and they will fall apart spontaneously over time. So even though the control rods were inserted, stopping the reaction, the chain reaction of uranium, the rods are still going to generate a certain amount of heat that dies off as those decay products themselves decay. Then an operator turned off the emergency core cooling because he mistakenly thought that the reactor was full of water, so that led to the rods getting too hot, the cladding around the rods melting, and a partial meltdown. 1/3 of the nuclear material in the core melted. That fell to the bottom of the steel containment vessel, but did not eat its way all the way through the bottom of the vessel. So that's why there was very modest leakage of just some radioactive steam. As we saw, I mean, the net result, if you use the linear model for cancer, how many extra cancer deaths would have been caused by all the radiation exposure that people around that nuclear power plant were exposed to? It's 1. Okay, a more serious event took place in Chernobyl in 1986. This reactor was even more dubious in its design. There was an explosion and fire, and in an effort to put out the fire, which was scattering the radiation, dozens, I think the story is 30 firefighters were exposed to several sieverts of radiation as they were putting out the fire, and of course then they succumbed to radiation sickness. And this has been much studied. This is the trajectory, the way the winds happen to be blowing, taking the radioactive fallout from Chernobyl here and sending it up to Scandinavia. And so it was, a lot of radioactivity was found in the milk of reindeer up in Scandinavia. The best estimate of the International Atomic Energy Agency is that the 0.6 megasieverts was what this population of 100 million people were exposed to. So if we use the linear model, then that would predict between 10 and 24,000, depending on who's doing the estimate of this number, but that's the ballpark, for how many extra cancers will be caused. People will get cancer and die because of this radioactive cloud. So that was a pretty significant event. Now, people get cancer anyway, and the normal number of cancers that you'd get for reasons that we don't understand in that population would be about 20 million. So it's statistically impossible for us to find that number in this number. But there is evidence, quite strong evidence, to show that children, especially in the region around Chernobyl, got thyroid cancer at elevated rates, something like 4 times more than people who hadn't, children who hadn't been exposed. And they were not given these potassium iodide tablets to safeguard their thyroids. And so that's why it's important for the Japanese who are nearby to take that. Okay, now getting on to how the reactor works. So in a reactor, I'm leading up to why a reactor and a bomb are perforce different things, and why a reactor cannot become a bomb. So in nature around us, on this planet anyway, uranium comes in 2 primary isotopes. 238 is much more common. 99.3% of all the uranium that you find, and it's all around, is this more common isotope. Uranium-235 is at about 0.7%. And at that level of natural radioactivity, you can't even make a reactor using regular water. If you want to go up to Canada and make a reactor using heavy water, then you can use unenriched uranium. But we don't, and so uranium-238 is sitting here. This plot is showing the, as a function of the energy of an incident neutron on 3 different kinds of nuclei, uranium-238, uranium-235, and plutonium-239. What is the probability that the neutron will be absorbed? And you can see below a very high number, this is 1 mega electron volts, which is a very large amount of energy. There is no probability for the uranium-238 to absorb the neutron. On the other hand, for uranium-235 in green and plutonium-239 in pink, as you go slower and slower, you use neutrons of lesser and lesser energy, the probability of interaction goes up. And you can think of that as just saying, if there isn't an energy barrier, then the slower you go, the longer you have to interact with that nucleus, the more likely it is that you will be captured. So in order to make a reactor go, we enrich the fraction of uranium-235, and then we have to slow the neutrons down so that they will get captured. In the kind of reactors at Fukushima, the agent that is used to slow down the neutrons is water, regular water. And as the neutrons try to plow their way through the water, they collide off the protons in the water molecules, and that slows them down and thermalizes them so that it increases the probability that when they next encounter a uranium atom that they will be absorbed. That heats the water, and the water then boils, and steam is taken off to run a turbine generator. The steam is then condensed, and the water returned to the reactor pressure vessel. And at the Japanese plants, it is cooling ultimately comes from the seawater. So that's where the excess thermal energy is rejected. And in order to have control over the rate of the reaction, rods of material, including boron, that absorb lots of neutrons, can be inserted. And when those rods are inserted, there are not enough neutrons around to stimulate the chain reaction. However, as I mentioned before, and the control rods in the operating reactors in Fukushima were inserted as soon as the earthquake was identified. And so that shuts down the chain reaction in which each decay of a uranium-235 that has absorbed a neutron and then sprays out at least 2 neutrons, as soon as you reach a situation where one of those stimulates another uranium-235 atom to decay, you have a sustained chain reaction. And you can adjust so you need to moderate the neutrons in order to increase the probability that one of those 2 neutrons is going to be effective, and then you can use the control rods to soak up the neutrons and shut down the chain reaction. That was done. But as I mentioned before, as the reactions proceed, you get all these different fragments, most of which are radioactive and decay with their own various half-lives. And so the rods continue to generate heat. And this is the profile. As soon as you turn off the reactor, now this is a typical size reactor, 3 gigawatts worth of thermal energy to produce 1 gigawatt of electric power. Efficiency is about 1/3. And just before inserting the control rods, about 7% of that thermal energy is released by these fission fragments decaying. And then as time goes on over the course of minutes, days, and years, this is 5 years later, that amount of power released decays away. So while this is happening, you have to keep the rods cool, otherwise they will heat up and melt and potentially release the radioactivity that's tied up in the fuel rods. So they're stored in swimming pools at the reactor after they're removed from the reactor vessel and kept that way for years. And this is what the reactor looks like at the Fukushima plants. So here are the rods in there, and there's up here a swimming pool. And when it's time to remove spent fuel rods and put them to cool down in the swimming pool, they flood the entire top area here so that they can hoist the rods, move them over, and deposit them in the swimming pool without having them leave the water. The water keeps the radioactivity down so the workers are not exposed to excessive radioactivity. That's why the pools have to be up high in the reactor building, and some folks were speculating that if you imagine an earthquake of the magnitude coming, you could imagine a fair amount of water sloshing out of pools that are up high rather than down lower. Okay, so there have been explosions at the inside the reactor buildings coming from hydrogen that is produced when the zirconium in the cladding of the fuel rods gets hot enough, like 4,400 degrees Fahrenheit, then this reaction takes place with the water surrounding them, producing hydrogen, which can then explode. And so one of the things that they've been learning is that they really have to have a means of venting that hydrogen. So can a reactor, it can melt down, in which case the fuel is melted and puddles at the bottom, and if it's hot enough, and it easily can be, that can eat through the bottom of the containment. And that's not a good thing, and that's certainly what happened in Chernobyl. But you can't get an explosion like in a nuclear bomb because the neutron flux isn't high enough. If it starts to explode, it will fly apart, and that suppresses the reaction. But in fact, the neutron flux is not great enough to cause an explosion. In order to get a uranium bomb, you have to enrich the quantity of uranium-235 to about 95%. Natural uranium is at about 0.7%. It has to be enriched to something like 2.8% for use in a nuclear power plant. So there's too much uranium-238, which absorbs the neutrons and shuts down the chain reaction. Can't get a bomb. Okay, so where are the dangers coming from? We mentioned iodine-131, and that one isn't the worst. It's the worst early because it has a half-life of 8 days, so as long as we, take precautions, particularly for children, load up those thyroids with healthy iodine, not radioactive iodine, they'll be fine. There are two principal species to worry about. Strontium-90 and cesium-137. Strontium sits here in the second column, and I don't believe, I got a chemist in the audience, he can correct me if I'm wrong, but I don't believe we need a whole lot of strontium in our bodies, but we do need calcium. And chemically, the strontium looks a lot like calcium, ends up congregating in the bones, and when it decays, causes problems that way. And similarly, cesium-137 is an alkali, and we don't need that, but we do need the potassium. And cesium masquerades as potassium in the body, and since the body then takes up the cesium, the decays would take place inside. Now, just to illustrate, this is a sample of cesium-137. It's encapsulated. It's not particularly dangerous to me since I'm not going to swallow it, and I really advise you not to do that either. And this is a Geiger counter that's looking for the radiation. Right now my body is shielding it, but if I bring it up here, the gamma rays that are being emitted by the cesium-137 can readily be detected. But this level of radiation is very modest. It's just annoying, so I'm going to turn that off. Okay, so what about these observed radiation levels? And these fluctuate a lot. On March 15 at the main gate, 11.9 millisieverts per hour. Okay, we're keeping in mind that we normally get something like 10. I'm sorry, that the number I want to keep in mind is the 3 sieverts, which gives a 50% chance of death. So we want to stay orders of magnitude below that. So this is not, I mean, it's definitely an elevated level, and it's cause for concern, but by 6.5 hours later, it was down to 0.6 millisieverts per hour. This is the level on the 17th. Now, some of you may have heard that we detected radiation from the Japanese nuclear disaster in Sacramento, and a minute quantity of xenon-133, the dose 1/1,000,000th of normal background. So yes, We did detect it because we have very sensitive detectors that are trying to monitor for nefarious nuclear activity elsewhere in the world, but that is no cause for alarm. In Tokyo, on the 19th, in the tap water, the level of radioactive iodine-131 was measured at 1.5 becquerels per kilogram. A becquerel is 1 decay per second. So this is very small. The tolerable limit is 300. Now, the biggest reading happened that I saw, and the New York Times was talking about it this morning, that workers at, I forget which of the reactors it was, they were not wearing full body protection. The shift before had been in with boots that were not high boots, and they didn't have a problem. So this shift went in, and 2 of the 3 workers had radioactive water spill into their boots. This is water that has clearly been contaminated by compromise of the fuel rods, and they were exposed to beta radiation and were burned in their feet and ankles by being exposed to about 0.18 sieverts. So they have been taken to hospital and are treated, and that's in some measure this is ridiculous because the people that they have working there need to be properly equipped. If there were a meltdown at the reactor, sort of a worst-case scenario, this is the level of exposure in REMS. And remember, we get to divide that by 100 to get to sieverts. So this one, at half a mile away from the plant, if things melt down and go terribly wrong, that's 54 sieverts. So that's death for sure. And this is the zone of potential damage. We're out here at 50 miles, which is the zone that the American government has recommended our expats evacuate. And this dosage level is down there at 0.1 sievert. So it's not apt to cause a great amount of harm, but it is simply precautionary. The Japanese government is now, as of today, encouraging people to evacuate farther and farther away, which suggests that things are long from being under control at the reactors, which is very unfortunate. But so far, there haven't been tremendous releases of radiation. So, as I mentioned before, from the Chernobyl reactor disaster, about 10 to 20,000 cancer deaths are expected over the next, the 60 to 70 years since the disaster in 1986. By contrast, just in this country, 10,000 deaths per year are attributable to the particles released from burning coal. And these are some numbers for traffic accidents. This one's really fun. So the airlines will tell you that they're 12 times safer than train because they will measure the safety in per passenger mile, whereas the bus companies would much prefer that you count per trip. Bus trips are much shorter, and then the statistic goes the other way. It's 30 times more dangerous to ride in a plane than it is to ride in a bus. But in any case, those are very small numbers, and usually they don't get in the way of our flying. Okay, so what should we be doing? Since probably the 50s, we've been worrying about the permanent repository for spent nuclear fuel. And for various geological and political reasons, the government settled on Yucca Mountain in Nevada. It's about 100 miles away from Las Vegas. And much work has been done exploring its feasibility as a permanent repository for the most radioactive of our wastes. President Obama made a deal with Harry Reid to squash that, and at the moment, plans for depositing waste there are on hold, if not totally dead. And as far as I know, I don't believe there is a country in the world that has an infinite term solution to the radioactive waste problem. I don't think France does it right. I don't think the Scandinavian countries or Germany does it right. Japan certainly doesn't right, and doesn't do it right, and they were overloading their pools. And we don't do it right either. We have at the moment all the spent fuel rods sitting mostly in swimming pools at the site of the reactors, and the pools sometimes have 4 to 5 times more spent rods than they were designed to accommodate. But we know a way that is quite good for on the order of hundreds of years, if not thousands, and that is to dry cast store the spent fuel rods, encasing them in glass. And so the NRC commissioner argued before becoming commissioner that we ought to be doing that, and perhaps one of the benefits of this disaster may be a more serious conversation in the country about moving to dry cast storage of our waste. They do some of that down at San Onofre at the nuclear power station between us and San Diego. Another point that Frank von Hippel was talking about in the New York Times a couple of days ago is that he's argued for years that we ought to require filtered ventilation from the containment structures in our reactors and the Japanese reactors. They have had to release steam, radioactive steam, to the environment because pressure was building up, because the water was, boiling, and they were not able to provide cooling. If they had in place these filters, then the amount of radioactivity released to the environment would be very much reduced. That sounds to me like a very modest expense. Naturally, of course, it's opposed by the industry. And really, there needs to be a better separation between the Nuclear Regulatory Commission and industry. Right now, it seems that the commission will do more or less whatever the industry asks. So, frankly, I'm not sure. I don't know the answer to this one. I think what we're doing with overfilling the pools is silly. We ought to stop that. We ought to do dry casking. We ought to have a centralized repository, probably in Nevada. Apparently, there's some lovely salt mines in Louisiana that haven't been bothered in forever, that would be a lovely place to put this stuff as well. But a part of me thinks that more research is going to figure out how to get energy out of neutering these wastes. So finding the appropriate ways to bombard them with energetic particles so that you basically cause rapid decay of the species that pose the long-term problem. There's international research being done. Nobody has a solution to that, but nobody, I don't think, believes that it's beyond possibility. So it may be that we'll want to dig all this stuff up again to use it. So I will leave you with just some sources that I found particularly useful in trying to bone up on this sort of stuff, and I will do my best to answer any questions that you may have. Yeah?
Just it's interesting to know for China, reports about 24,000 deaths a year from cold. About what we get. But it is on preventing the outside
Right. And there are new improved designs for reactors. I don't know whether, I mean, I'm perfectly happy to be agnostic about whether we should be going ahead with nuclear power. There should be a nuclear renaissance. But let's at least argue based on facts. And I've heard, I think, a fairly credible argument that nuclear power isn't going to win just based on cost, that solar and wind and other renewable forms are ultimately where we're going to go, and they will be cheaper in the long run. On the other hand, they tend to be intermittent, and we don't have a great solution on the storage problem, and that's one of the advantages of nuclear reactors, is that they have a pretty good uptime. Yeah. Yeah. Chernobyl? That one. Yeah. 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 Mm-hmm.
So how concerned should I be about all the radioactivity?
I think you should be concerned to watch what's happening. If they manage to dump enough water and get control of that whole complex so that you can watch what the radiation levels are and you understand why, presumably, unless another 9.0, failing that, and probably there's good geophysical reasons why that ain't very likely, that you should be fine. But I would, you definitely want to monitor. But I was talking to my mother, and I shouldn't identify who this person is, but she has a small son and was worried about the radioactivity of being here in California, and so flew her 1.5-year-old son to the East Coast. Well, she got more that kid got way more exposure to ionizing radiation for taking that flight than he did by staying put. So I think we get more nervous about things that we don't understand and that potentially have great risk and great downsides to them. And there has been a period of time when the nuclear industry, the government associated with nuclear power, didn't deal very straight with people. They were doing tests in Nevada and poo-pooing the fallout issue. But at the same point, there's a lot of very solid scientific work to understand radioactivity, understand the time evolution of this disaster. So if this happens, it's going to be a great tragedy. I mean, it is already a great tragedy. Clearly, the tsunami killed way more people. What's the count? Is it up to 10,000 or 20,000? 10,000. Yeah, 17,000. And, it may well be that we hear in the next week or two of deaths caused to these workers for the exposure that they had, if they were underestimating what that exposure was. But this would be terrible because the half-life of those species I was talking about, cesium and strontium, is about 30 years each. So if you have to wait until the radioactive level decays by 1,000, you're going to wait 10 half-lives. That's 300 years. So around Chernobyl, there's a region that is not habitable unless you're a risk taker for 300 years. Yeah. 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 Yes. Yeah, now it's back down. Yeah, that could be. I was drawing from a whole pile of sources. Let's see. Nope, higher. Yeah, so that 300 becquerels may be what's acceptable for adults and 100 for children. I'm not sure. Yeah. So they warn people not to, to use bottled water for, yeah, right. Yeah, and that was presumably a spike from the way the wind patterns are when it blew radioactivity back towards Tokyo as opposed to out over the ocean. Yeah, the Sun in China was informed that there was a run on iodized salt in China, and actually all salt, because there was a scare that if that fallout falls in the ocean, that will contaminate the salt. So people went out and bought a lot of salt, and then the stores didn't really want to take it back when they realized that. Yeah. Yes. Yeah. Right. So if you get a dose of 8, you don't have time to get cancer. You will die long before you get cancer. But if the linear model is correct and we distribute those 22 sieverts, maybe, you know, how much would you take? Okay, so you get 22 millisieverts and he gets 22 and so forth, and you just spread that out over a population, then the expectation is that one of them will have contracted one more cancer than they would have otherwise. Yeah, that is weird. It's a weird consequence of the linear model. Yeah. Well, if you don't keep the dose low enough, then your worry is not cancer. You will be dead long before you're going to develop the cancer. But the linear model says it doesn't seem to matter how I partition that among different people, provided that I keep it below the level that is going to cause them radiation death. And so it's just suggesting that it's the total dosage distributed among humans below radiation sickness level. That's what matters. Yeah. Oh, boy. It's been fluctuating like mad. And there have been periods when there's releases of radioactive steam that they have to evacuate everywhere. So it's made it very difficult for them to get control, because the electricity was knocked out to run all the pumps. So they've now managed to reestablish connection to the AC grid, but some of the equipment isn't working, and then some of the challenges of getting close enough to do the repairs are still daunting. So it's not clear that they're going to be able to avoid having at least one of the reactors melting down. Which would be terrible. Yeah. Sure. Yeah. Yeah. Okay. So the rods start out with mostly uranium-238 and a little bit of uranium-235 in a ceramic, in these pellets that are slid down a casing that has zirconium and other metal alloy. And as the reactions proceed, then uranium atoms fall apart and they produce these cesiums and iodines and various other decay products, which themselves are radioactive. And some of those uranium-238 atoms absorb a neutron and they become a product that decays into plutonium-239. So over time, the population of uranium-235 atoms goes down. The population of plutonium-239 goes up from nothing, and you have all these other decay fragments. Now, the half-life of plutonium-239, I think, is about 24,000 years, so that's not particularly hot, but it can be chemically separated and then used either for a bomb or as a fuel for a reactor. The other fragments have their own, different pathways of decay, releasing energy all along the way. And that's why the cooling curve is not monotonic. It cools as, you have an early release of the things that are really radioactive and decay very quickly, shedding their energy. But once they're gone, and then you have a further cascade. So it's inside the fuel pellet, you have decays of these fission products, the smaller nuclei that were created when the uranium fell apart, that have to go through their decay sequences to arrive at something stable. And so as they're releasing that heat, if you don't take it away, then it will heat up. If it heats up too much, it melts the zirconium, and that can then create this very dangerous puddle of molten radioactive material falling to the bottom of the reactor vessel. And that's what a meltdown is. Yeah, one more question, and then I'm getting the high sign that we're going to have to evacuate. Hopefully not from either an earthquake or a nuclear catastrophe. Yes? Yeah, so that's a tricky one. It depends on who's talking. It's not in the respect that once you use up the uranium, it can't decay more than once, although there are such things as breeder reactors. So in the United States, since the Carter administration, we have not pursued breeder reactors. But a breeder reactor allows you to use that uranium-238, and remember, it's over 99% of what's available, and convert it into plutonium that you can burn in the reactor. So you can use the reactor to produce energy and produce more fuel. You can get about 140 more uses, more cycles, 140 times more energy out of the uranium fuel if you recycle. We don't, but we could. We don't do it because extracting that plutonium is deemed to be a proliferation risk. So once you can, it's not easy, but it's much easier than enriching the uranium. So you can chemically separate plutonium from uranium, whereas you can't chemically separate isotopes of uranium. So it's much harder to do that. You need all those centrifuges and so on. But you can isolate the plutonium, but then it's easier for people to make a bomb out of the plutonium. And so we haven't done it. Japan does it, and one of the worries is that they've done that in one of the reactors that's having problems, and so they're using a mixture fuel of uranium and plutonium. And that's sort of a novelty here, apparently, in terms of dealing with what's coming out of it. So our hearts go out to our friends in Japan. I have been in correspondence with my Japanese host father, who is embarrassed that he didn't even feel the earthquake in Kyoto, although other people in Kyoto did. But I think they're enormously resilient, and with some of our help, hopefully, they will be on the road to recovery. So keep your fingers crossed so the damn thing doesn't melt down more. Thank you for coming.